Hi students, welcome to Physics for Everyone classes. This is your satish. So in this video, we can see the rotating of the rod which is placed in a uniform magnetic field. And here we are going to find how much is the induced EMF which is developed across the rod. Let us see the topic. The concept is rotating of the given rod in the uniform magnetic field. So initially we need to place a uniform magnetic field in the given region. Let us see a uniform magnetic field which is placed in a certain region along the z-axis. We can say perpendicular to the plane. We can call it as the z-axis into the board. So the cross indicates that the magnetic field is acting into the board. Here in this region, we need to consider a conductor, or we can say a metallic rod in this manner. So OA is the given conductor. Here, the rod is being fixed at a particular position. Suppose at point A, we are fixing the rod. And this rod is going to rotate in the XY plane like this. If you take, this is the OA rod and it is moving in the XY plane in this manner. Now, about this axis, you can say about this axis, this rod is rotating with a constant angular velocity omega. So what I am taken here, a uniform magnetic field which is set into the z-axis, where I consider a uniform metallic rod OA which is placed in XY plane, and at point A the rod is being fixed about this axis. This OA rod is rotating in the XY plane. The axis of the rod is along the z-axis. There you can see the axis of the rod is along the z-axis. About this axis, this rod is rotating in the XY plane, which means this rod is cutting the magnetic field. Whenever the rod is cutting the magnetic field, there are always exist induced EMF across the ends of the rod that we want. So in order to calculate induced EMF, in the last videos we have seen the induced EMF across the end of the rod which is taking along the x-axis with a constant velocity v. Then we got the expression E is equal to BLV. But here the difference is that the rod is not moving totally. It is rotating about a certain axis. So that is the reason we cannot take the same formula BLV. So instead of that, so what I am doing here, the entire length of the conductor is being divided into smaller parts. We can divide the entire length OA into smaller parts. So where I am taking a smaller part which is named as dx. There you can see this is the smaller part which I am taking. Its length is dx, and this part from the axis of rotation, the distance is being taken as x. This is the distance x, and as it is rotating in the anti-clockwise direction, every element of it have a velocity. Let it be taken as v, which is called as the tangential velocity. How you will get, if you know the distance from axis to that point by the relation v is equal to r omega, we can get the velocity of each and every part of the conductor. As this part dx has a velocity v, we can write v is equal to x into omega. As you know, v is r omega. We have studied in circular motion. So it comes as V. The velocity of this part dx is equal to x, the distance from axis of rotation to this small element, into angular velocity. Have you noticed every part of it have a constant angular velocity, but as the linear distance changes or the radial distance changes, correspondingly the linear velocity also changes, which means different parts of the conductor has different linear velocities. So this is the reason the expression doesn't come as BLV. So instead, if you have taken a small element and this element is moving with velocity V, this velocity vector makes exactly 90-degree angle with the magnetic field vector, and also this velocity vector is perpendicular to the assumed small element dx. So there we can use the formula induced EMF across this small element is taken as dE. So what is dE? dE is the induced EMF across the small element dx, which is equal to B. Instead of L, we need to take the small element length, which is dx, and whose velocity is V. Then we have got V is equal to how much? X omega. So there can substitute d is equal to B into dx into what is V? V is x omega. And you can rearrange this one d omega into x into dx, which is equal to d. So this is the induced EMF across the small element dx. But we want the total induced EMF across the entire length of the conductor from O to A, whose entire length is being taken as L. So L is the length of the conductor OA. So to get the total induced EMF, we are familiar with some mathematical tools. There we need to use the integration between the two limits. From x is equal to 0 to x is equal to L. If you integrate this expression, you will get the total induced EMF. So let us calculate. So integrating on both sides, between the limits x is equal to 0 to x is equal to L. What is integral of dE? The total induced EMF you will get E between the ends OA, which is equal to B constant, which is set into along z axis. It doesn't change. Uniform magnetic field B. Angular velocity of the rod, which is also constant omega. Integral of x into dx from x is equal to 0 to L. What is integral of x dx? Another formula, integral of x power n dx is x power n plus 1 by n plus 1. Then we have the power 1. They can write b omega into what I told? Integral of x power n dx is equal to x power n plus 1 divided by n plus 1. So here the 1 is there in place of n. There you will get this expression x to the power of 1 plus 1, which is 2 divided by 2 between the limits 0 to L, which is equal to b omega divided by 2. And first we need to take in place of x L minus the lower limit, upper limit minus lower limit. There it comes as L square minus 0. So which is equal to b omega L square divided by 2. So you got the result. The total induced EMF across the entire length of the conductor OA. You got the result? B omega L square by 2. If you see, this is the potential difference. The next question is that at which end you will get the positive potential and where you will get the negative potential. You got the magnitude. This is the magnitude of it. And in the earlier sections we have seen in the conceptual videos, to know which point is the potential, there I told you V cross B direction is important to us. What is V? The velocity of the conductor, in which direction the conductor is moving, and B is the magnetic field direction. And here also you need to take V cross B direction, in which direction it existed. To that side you will get the positive higher potential, the other side comes as the lower potential. Let us try to find either Y is positive or A is positive. Let us see. So you can see dx element has a velocity which is in xy plane, is moving in this direction. Then you can see this is V bar. And B bar is into the board. This is along the z axis. So V to B we need to travel. Then you can see clearly V to B. When the curl of fingers, the thumb is acting towards the point O. There you can see V cross B, the thumb is acting towards the point O, which is the axis of rotation, and this end of the rod, where it lies on the axis of rotation, you will get the higher potential. The point A comes as the lower potential. There I can write the potential difference between the points, or you can write it as EOA, which means EO minus EA in better way. The potential difference between these 2 points, which is equal to B omega L square divided by 2. So what is the use of V bar cross B bar? The V bar cross B bar gives the direction. In which direction you will get, that point comes as positive. Here it comes as O. The point O comes as the positive potential. Therefore, the point A, where you will get the negative potential or the lower potential. So what we got here? When a conducting rod which is being rotating about a certain axis in the uniform magnetic field, and the plane of rotation which is perpendicular to the magnetic field, there you will get a potential difference across the ends of the rod, or else we can say this conductor is been acting like a battery of EMF. You got the result B omega L square by 2. And the second part is that at which point you will get the positive and which point you will get the negative potential. For that, we need to consider, this is the most important point as I'm mentioning you, to judge which point is higher potential, which point is lower potential. Always stick to this. First you find V cross B direction. So V bar, this is the direction of V bar, and B bar is into the board. So V cross B, where the thumb is showing in which side, that point, that side point comes as the higher potential, the other point comes as the lower potential. So that's about the induced EMF across the ends of the rod. Later we can see for different orientations how to find which point is higher potential and which point is lower potential. And I am taking here the magnetic field again into the board, which means along the negative z axis. And the conducting rod I am placing in the xy plane as usual. This is the point O and here is the point A. Now I am trying to rotate this conductor about this point. This is the fixed point, Y is the fixed point, and where the axis is along the z axis, about this axis, this rod is rotating. Now I am rotating the rod in clockwise direction like this. About the axis, this rod is rotating with a constant angular velocity but in the clockwise direction. For this, the things will change, where the potential difference will remain same, but where you will get the higher potential and where you will get the lower potential. Let us check once. And the same concept, we need to take a small element which is dx, and whose velocity of this part velocity let it be taken Vx. You can see here the Vx is acting in this direction. It is an xy plane, downward direction, and magnetic field is into the board. There you can see V bar is in this direction. You can see my hand, the V bar is in this direction, and magnetic field is into the board. When you turn the fingers from V to B like this, the thumb is acting towards the point A. So V cross B direction represents the positive potential point. Now the positive potential point comes in which side? As at the point A. The point A comes as the higher potential point and the point O is the lower potential point. So there you can see clearly if the magnetic field is into the board and the given conductor is rotating is in xy plane in anti-clockwise direction, there you will get at the point, at the origin, where the rod is about to rotate, there you will get the higher potential point and the far point comes as the lower potential point. Here, we are rotating in clockwise, there we got the reverse polarities. At the point O, we got the answer, lower potential point, and the point A got the higher potential point. So let us see one more diagram. Here I am changing, this is the figure 2. Let us see the figure 3. So in this diagram, I am changing the direction of magnetic field. Here I am taking the magnetic field is acting out of the board along the positive z-axis. There you can see the dot with circle represents the magnetic field is acting out of the board. This representation indicates the magnetic field is acting out of the board. And here again, you take a conducting rod like this. And this is the point about the rotation is taking place. There you can see the rod OA, which is rotating with a constant angular velocity in the anti-clockwise direction. And take the small element dx whose velocity is v. And if you see, v bar is on the plane. Okay, this is the v bar. A magnetic field is now acting outward direction. So we need to take the curve in such a way, v bar, the 4 fingers is along v bar. From there we need to rotate towards B. Towards B is towards you. So V bar cross B bar. The thumb is acting towards the point A. So we got the result. So V bar cross B bar direction is acting towards A, which means that point A, at point A you will get the higher potential point. So this point comes as the higher potential point. Now the point O is the lower potential point. The last diagram, you can see the figure 4. The same. The magnetic field is acting out of the board. There is no change in the direction of magnetic field. But we are taking the rotation of the conductor about the point O in the clockwise direction. There you can see in the clockwise direction. This rod is rotating in the xy plane in the clockwise direction where the magnetic field is out of the board. Now, we need to consider the small element dx whose velocity is vx or v. You can take. So, to find the potential point where it is positive, again you need to take v bar cross b bar. This is v bar. How you can take? So, it's been difficult. So, you need to take v bar along this direction and b bar is acting towards you. So, you take v bar cross b bar. You got the point? V bar cross b bar. So, curl of the fingers from V bar to the B bar and thumb is acting towards the point O. So, there you got the point O represents the higher potential point and the point A is the lower potential point. So, in this way, for the given magnetic field and for the given rotation of the conductor, there you got the result. Induced EMF, the magnitude is how much? B omega L square by 2, where B represents the magnitude of the magnetic field, which is fixed in one particular direction, omega. We are setting the rotation of the conductor with a constant velocity, so omega is constant. L. L is the length of the given conductor, and there you can see in which direction it is rotating depending on that, and there which point you will get the higher potential point or the lower potential point divided by 2. So the magnitude is constant for all the four cases. For four different diagrams I was given. For the four different diagrams, we will get the same result. The magnitude is constant. How much? B omega L square by 2. Where you got the difference? As you got the difference, the which side you will get positive and which side you will get negative. There you will find the difference. But to check that point, we are taking the help of the cross rule, which is V bar cross B bar. I am telling you again, in which direction the V bar cross B bar shows, that side point comes as higher potential point, the other point comes as a lower potential points. So that's it about induced EMF across the rotation of the conductor. Later we can see some applications related to this concept.